Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm delighted to have Oded Regev, who's from none of the institutions listed on this thing, but who's here for a couple of days. He's going to give a talk today on lattice-based cryptography, and I'm glad to see so many of you here. Tomorrow he's giving another talk at the same time in the same room, but those of you on that side of the room may not be able to hear it because there'll be a barrier in between. For those of you who are Oded really needs no introduction here. He's worked on a variety of topics, and tomorrow's will be completely different from today's. But so I'll turn it over to. Tomorrow is on. Yeah. What?
Some of our work with Thomas Vidic on Grothendieck inequalities, SDPs. Probably different audience.
So approximation algorithms for SDPs,
yeah,
and rounding and quantum connections, yeah, and so on. So Oded has a sort of a wide spectrum and gives, it will be a much more informal talk tomorrow. Okay.
Yeah.
All right, so over to Oded.
Okay, so thank you, Madhu. Thanks for the invitation. So I thought the plan for today is to give kind of a very high-level overview of this area. There won't be much, many technical details, and feel free to interrupt me. So I just want to give you kind of an overview of this area, and I'll start with a very short introduction, and the second part of the talk should serve some kind of warm-up. It's something cute. Just I want you to, this is something nice that later you can tell your friends about, and then we'll go to the main part of the talk. This will be about lattice-based crypto. So I should start by saying what lattices are all about, and why we care about them. So this is a kind of my attempt to render a two-dimensional lattice. So this lattice is a set of points with this periodic-like structure. It's a mathematical object, a geometrical object, and more formally it's defined in this way. You take n linearly independent vectors, say v1 up to vn in n-dimensional space, and you just take all their integer combinations. So it's a bit like linear span, except you take integer combinations and not just integer combinations. Okay, so there's the picture over there, shows a small part of a lattice, right? As you can imagine, it goes in all directions to infinity. I take two vectors, v1, v2, and then take all the combinations, twice v1, v1 plus v2, and so on and so forth. So this seems like a natural thing to look at. It has, I'll mention later, lots of properties. You'll see this during this talk. V1 up to Vn, I would call these vectors a basis of a lattice. This is a two-dimensional lattice. In general, we care about higher dimensions, like say 500-dimensional lattices. This is the range that we're interested in usually for crypto. Okay, so what's interesting about these lattices is that they're
to n, so it's always Rn and Vn?
N is equal to n, in the sense, yeah, n is equal to n. You don't need that. You can consider what's known as non-full rank, but it doesn't add really much generality. So n equals n, yeah. So the basis is not unique, and this is what makes this so interesting for computational purposes. You could generate the same lattice I had before. Actually, you can generate in two ways. You can generate in many ways, but at least in these two ways, you can take either v1 prime, v2 prime, which is the way you would anyway, you would expect to generate this lattice, but you can also take a different basis. You can take v1 and v2, which is kind of much closer together. And the reason to generate the same lattice is because you have cancellations. You can take, in this case, 3 times v2 and subtract 4 times v1. And you can see it generates here that it generates this vector. So if you add and subtract, you end up with the same short vectors as before, like v2 prime, v1 prime. So in short, there are lots of bases for a lattice, and this is kind of crucial. This is what makes it hard for computation, and this is what makes it useful for crypto applications. Okay, so The history is quite old, actually dating back to the early 19th century. Work by Gauss who actually already gave an algorithm, one of the earliest algorithms for solving certain lattice problem in 2 dimensions. This is Gauss's algorithm from 1801. Later work by Hermite and Minkowski. And it's a nice area. They look a bit unhappy, all these mathematicians, but it's a nice area to work in. I think it's because of the work.
Invented the probabilistic method, right? In this series.
In this work, yeah, you can. Yeah, I don't know if he formulated this way, but
It's almost
true.
like
There's
that,
proof.
right?
Yeah. Indeed, he looks the happiest of all three. Yeah. Makes sense. So there's been lots of work, and their interest is actually different. It comes from number theory applications. We'll actually care about slightly other aspects. Maybe Gauss is the closest to us. One thing I have to mention, because any talk on lattices, one has to mention this. This is the celebrated LLL algorithm. It's not something, here they're even happier, I don't know if you can see. I don't know if this is something, I won't use it in the talk, but that's something I have to say. This is algorithm, very famous algorithm by Lenstra and Lovász in 1982. What it does is essentially, the input is a lattice in the form of n basis vectors. And what it does, it finds somewhat short vectors in this lattice. Somewhat short is actually not so short, it's actually exponentially long in the dimension, but still for many applications, it's a great algorithm. It has lots of applications in many different areas. So it's, for instance, you can, and this was the original application, you can factor polynomials, say, over the integers. You can solve integer programs. If you have an integer program in a fixed dimension, this is, through such algorithms, this is how one solves them. So it's an integer program involving only a small number of variables, but still numbers might be big in the integer program. It's not, a priori obvious how to solve such things, and this is how it's usually done. Another cute application, related to the first bullet there, is what's known as finding integer relation. So I give you a number, so you do some experiment. Right? You do some numerical integral, something, you get this number 6.7320508, and you're wondering, maybe it's a nice number, maybe it's square root of 17 plus 5 to the power 1/3, some nice algebraic number. Does anyone know? Does this ring a bell? Mathematicians here that might sometimes people. It's yes. Right. So it's 5 plus square root 3. This was an easy one. But you can do any algebraic number. This is like a degree 2, but you can do higher degree algebraic numbers, and it really finds it. So you can do, like in Maple, Mathematica, you can give this approximation of algebraic number and spits out this number.
So it finds the minimal polynomial?
It finds the minimal polynomial, yeah. And the way you do it, you can take the powers of number and take integer combinations. Yeah. And more related to our work, it's been used during the 80s for attacking crypto system based on knapsack and certain variants of the RSA crypto system. Some very special cases of RSA. This is very nice work, and it kind of leads us towards the topic of today's talk. Yeah, I'm not quite sure which one is which. I guess the right one is one of the Lenstras. It's probably Arjen Lenstra. Yeah. Okay. So one problem, just to give a flavor of the kind of computational problems we care about, one of the prototypical problems is known as the closest vector problem. So the input is, again, a lattice in the form of n linearly independent vectors, in this case 2 vectors, b1, b2. But you also give it, in addition, you're given a point in space, not part of the lattice, a point u, and your goal is to find the nearest lattice point. So think of u as being close. I want to find that, that point next to you. How do you do that? This is the closest vector problem. And in general, it's a hard problem. It seems very difficult. The best known algorithms take time exponentially in the dimension. So if we're in dimension 500, it seems extremely difficult. But one observation, maybe exercise, if the point u happens to be inside the lattice, you can tell that it's inside the lattice. You can detect this. Does anyone see how? So it's easy. You essentially, you can invert the matrix or just solve for the coefficients of u in the basis bi, right? Gaussian elimination, and see if they're all integer. Just express u in the basis bi and see if all the coefficients are integer. This is if and only if u is part of the lattice. And somehow the difficulty here is that U is not quite there, and because the vectors B are so long, even though U is close, the coefficients all get messed up, and you won't see much. So just a flavor of why this is a hard problem. Yet, in the mid-80s, Babay suggested an algorithm that sometimes works, and the algorithm does the following thing. Assume you have a basis, and if the basis is nice, the algorithm works well. If the basis is not nice, the algorithm doesn't work so well. And the idea is extremely simple. Essentially, what we said before, if I have a point, I just write a point in this basis and round each coefficient to the nearest integer. So I just express the point in my basis. If I see 0.9, I just round this to 1. If I see 5.2, I round this to 5. And if you think about it, what it essentially does is something like this. It partitions the space into this, what we call parallelepiped. This is a kind of linear transformation of boxes. And each area like this is mapped to the point in between. So in this case, it does a pretty good job, this algorithm, because you see all the points here are mapped to the point in the center, and it's kind of right. It's not exactly right. Actually, points here are closer to this one, but it's pretty good. But this is only if you have a good basis. If you have a bad basis like this, picture looks very different. So it's actually a very bad algorithm because points that are here are still going to map all the way here. Okay? And this is kind of very bad because you're actually very close to the guy here. You're going to be mapped there. So, just I hope this gives you some intuition of why this problem is hard. Okay. So now this is the warm-up. I won't give too many details about it. It's just something that you can, one little thing you can take from this talk. So there's something called the GGH digital signature scheme. It was one of the early attempts to use lattices for crypto. What I'll show you today is actually that it had a serious flaw, and I'll show you how to break it. One reason I want to emphasize why there was this flaw is because there was no security proof. I mean, there was this construction that seemed to make sense. It seemed to be secure, but after after some time, turned out that this actually can be broken. I'll say more about this later on. But so once we get to the main part of the talk, I'll show you that there are constructions with a security proof that shows us that at least. Or I'll tell you more about this later. The idea is very elegant, a very beautiful idea. It actually was used later to construct secure systems. The idea was, as we saw before, CVP is hard, but if you have a good basis, if you are lucky to have this good basis, you can actually solve it pretty well. And this was the idea behind the signature scheme. So I won't assume you know anything about crypto. I won't assume you know about exactly how to define a signature scheme. I'll mention later what this really amounts to. This proposal of GGH was later taken, and using a brilliant construction that came from this mathematician from Hargrave Graham, Pfeiffer, Silverman, and White, part of the Entru company, they managed to get a very concrete implementation of this based on very nice ideas from algebra, and managed to get very concrete, nice parameters with signatures of length only less than 2,000 bits. This is quite important for application of signature scheme if you want to put this on a smart card or something like that. And the signing verification extremely fast, faster than all RSA-based methods. It seemed very promising. And there was IEEE group tried to standardize this. So there was lots of nice activity around this. And let me show you the idea around behind this GGH signature scheme. So what is a signature scheme? You have some kind of information, some message you want to sign. Imagine Microsoft wants to release some update. This is you want to sign this is authentic, and the way you would do this, you would select. As Microsoft, I have my own private key. I store this privately. No one knows this. And the private key is essentially just a good basis. I choose somehow. I'm not telling you how, but you somehow choose a good basis. Some autonormal-like vectors. And what I release as a public key is another basis, a very bad one. Like I perturb it somehow, I take very long vectors. Okay, there are ways to do it. I won't tell you how, but there are ways to release a very bad basis associated with this private base. This is not where the trouble lies. Okay? And the idea is the following. So I think of my message, the file I want to distribute, my email, I think of it as a point in space. There are standard ways of mapping a file into a point in n-dimensional space. This is, again, not so important for us. Just think of the message being just some random point in space. And the way I want to sign this message is by outputting a near lattice point. So my signature that I'm going to attach to the message is simply a nearby lattice point. And me, as Microsoft, I can do this because I have the private key, and I can run the Baba algorithm. I can just round the coefficients, and I get this nearby lattice point. So that's what I'm going to release. Each time I have a message, I'm releasing a signature, which is a nearby lattice point. Now, some of the clients don't see the private key; they only see the public key, right? But they can still verify this. They see, okay, here's the message, here's the file I just received. That's where it sits in the space, and here's a signature. All I have to do, I have to check two things. I have to check first that the signature is really a lattice point, but that's easy. We did this before, right? We just compute the coefficient, see the one integer, and then I measure the distance. I subtract the two vectors and look at the norm. They have to be nearby. Very easy, and seems to make sense. It's definitely correct. The only question is whether it's secure. Okay. So questions? Is this clear? Okay. Good. So what we showed is there's actually an inherent security flaw here, and I'll show you in a minute where it lies. And we implemented this. It was actually I think first and last time I had a chance to implement something. And I think both versions. And we only needed 400 signatures to recover the entire secret key. It was actually surprisingly efficient. We didn't expect it to be so fast and so efficient. So after receiving 400 signatures using this EntroSign proposal, you could just get the whole secret key. And it was extremely fast. It took a couple of minutes, and that was 3-4 years ago. So I guess today would be even faster.
So the EntroSign is based on GGH?
Right. EntroSign is essentially, for our purposes, just GGH. But there's a very clever implementation of GGH that makes it so efficient and so small.
So it's efficient in the sense that the running time of the encryption is the
running time, and more importantly, also the size. The size of the signatures is very small. They use essentially cyclic-like lattices to reduce the size of things, because the GGH originally is quite wasteful.
What do you mean by signature?
So here,
just go back. Yeah.
so signatures are. So I assume after receiving 400 updates, each signed separately, I can tell you what the secret key is, right? So I need some signatures.
So maybe you should tell us what's the semantics of a signature.
Okay, so a signature scheme given should be able to do the following. You have a way to choose a private key, you key privately, and you release a public key. And what you're supposed to be able to do with it is, given any file, you're supposed to compute something based on your private key, such that when you release this, anyone can tell, right, this is signed by you. And no one should be able to forge this. So what we're doing here, essentially, not only forging signatures, but even worse, we're extracting the private key. It's kind of the worst possible way of attacking. Right. Forging is a weaker attack. You might be able to forge some messages, not all of them, but this is really attacking the private key, and you can forge anything later. If I knew you were there, I would be more careful. So, but you made a point of sitting there. See.
There's a feature that there's a bunch of messages have the same signature. Because so that was something that was different than usual signatures. You're sort of envisioning, say, music or something where there's a little bit of changes, and you still want to have the same signature or finger.
So you're saying this is a good feature?
To begin with, it wasn't going to be possible to prove security in terms of message attack sense, because we knew that.
You mean the security proof?
Recovering the secret key is a different story.
Right.
So what I'm saying is we realized, in fact, we thought there was a feature. You see what I'm saying? So there was no intention. I didn't think you could actually prove it's secure in that sense if that was the future.
Yeah, but this is a happy end. I mean, the story, the idea turned out to be. Yeah. Okay, so here how it works, and the idea is this. Right, this is what Microsoft has. This is a private key. It allows Microsoft to sign messages, but I don't see it. Right, I only see this. I only see a message and a signature. So I see some random point in space, and I see the nearby lattice point. So what I want to do with this, I just put it aside. Okay, now I see another one. Another update comes. These days, it's kind of every day I get an update from Microsoft. So no offense. And then I just put it aside. I do it again. Another update comes, I put it aside. Another update comes, I put it aside. Let me know when you see a pattern. Okay, so after you do it a couple of times, so you see a shape, and the shape is exactly the shape of that parallelepiped that is hidden, by the private key. Okay, so this is the main observation that once you collect enough signatures and take the difference between the signature and the message, you essentially get points sampled uniformly from the secret shape. The shape is secret; you're not supposed to know it.
So the blue thing is the message.
The blue thing is the signature.
So
It doesn't really matter. You could do it both ways.
Yellow is the message.
Let's see. Yellow is the message. Yeah. The blue is the signature.
Okay, so in your picture, the yellow dots were all over the places, right? So you're sending different messages?
Yeah, so each time there's
Okay,
a new message coming.
Okay.
Right. And
So how's the message?
so message, think of it as a random point in space. Usually you have a file and you hash it into space, and usually it
You
results
can ask
in
for messages of your shooting here?
No. I don't need to assume anything. It just comes a new update, a new randomly generated message. I don't assume anything about the message. I just need to assume that it's sufficiently uniformly distributed, but usually that's the case because you apply some hash functions. Okay. So and then what you end up with is this question, right? So you're supposed to solve the following statistical equation. So you have a bunch of points sampled from n-dimensional parallelepiped. So in 2 dimensions, it's a parallelogram, and you have, this is a sample there. You have all these points sampled from it, and how do you recover the parallelepiped? And this is in 2 dimensions. In 3 dimensions, it looks like this. So this would be. I don't know if you can see anything. If you don't see, actually, it's good because it shows that it's non-trivial. But you can actually do it. I mean, given points, in our case, it was like in 500 dimensions. You can extract the shape of this parallelepiped. So you can try to think how to do this. There's some non-trivial things.
500 dimensions, and you recovered it from 400 points?
And 500.
Right. So this is somewhat of cheating because it's a cyclic. Lattice 400 actually translates to 400 times 500.
I see.
Yeah. So it's slightly
it's
more.
Sort of like quadratic somehow.
So
what's 400 times 500?
So in the case of Encryption, there's some symmetry in the lattice. So the shape has some symmetry. Once you get a point, also 500 other points are also there. So you can use all of them. Yeah. So this made it 400 and not 20,000. Okay. So I'm not going to tell you more about it because it's not really Eli, question.
The fact that they were clever made it worse for them.
The fact that they were clever made it.
The intro, yes.
Not so clear, because I mean, you just would have had to wait for 20,000 samples, but the complexity of your
Yeah.
algorithm might have been the same.
Yeah, actually, first we didn't realize the symmetry. We just did it with 20,000 samples, and later I think it was White who told us that actually you only need 400. You just use the symmetry. It's in terms of in practice, doesn't matter much. It's fine.
400 sounds a lot more damning samples. Sounds more damning.
Well, think of the number of emails sent by you or any company. And there are lots of signatures hovering all over the place. So that's true. 400 sounds reasonable, maybe 20,000 slightly less, but it's not good in any case for a signature scheme to be broken after 20,000. Eli?
200. It's 200,000.
200,000. Eli? No, try to make it sound nicer. No? Okay. So the problem is actually happy ending. The idea in GGH is a good idea, and this was actually made secure, provably secure, by a later paper using the ideas I'll show you next. So currently there are provably secure signatures. It's by Gentry, Pikert, and Vaikuntanathan, but it's not quite yet, I would say, as efficient as what we had before. But at least it's secure. Okay, so this kind of brings me to the main part of this talk. And this is kind of modern lattice-based crypto, how to do it in a provable way. Maybe I should have said this before, but maybe now it's a good time. It's better to say it now than never. Cryptography is everywhere, and we really want to have cryptography. It's in credit cards, passports, mobile phones. And as you probably know, everyone is using RSA these days. Websites, almost all applications these days use RSA. And kind of the goal of this project, this long-term project, is to kind of find some alternatives to RSA, and I'll try to convince you that we're slowly getting there. Maybe we already have a reasonable alternative to RSA. So how does the story start? It starts in the mid-90s, work by ITAI and ITAI work. Really seminal work. They made this brilliant observation, realization that you can actually use lattices to create crypto. It wasn't obvious until then. I told you before, people use lattices to break crypto. They use things like LL algorithm to break, some algorithmic tool to break certain constructions. And they said, actually, let's create crypto system based on lattices. It has some amazing properties which only in the last few years we fully understand. Some of this construction originally wasn't perceived as something that can really lead to something useful or practical. It was extremely inefficient. I think if you actually try to implement it, you would need keys of size some gigabytes. And of course, it would be extremely slow. It's not only the numbers are big, it's also kind of cumbersome to work with, and it seems very difficult to extend. I mean, you do something very specific, but if you want to do something slightly different, you kind of have to redo the whole thing. It seemed to be of purely theoretical interest and somewhat limited. And I think more recently there seemed to be a change, and kind of lattice-based crypto is becoming more mainstream.
But there's kind of an empirical question, which is if you generate one of these lattices,
right.
Is there some heuristic that works
well
on them, or is there a feeling that just for the first...
Right, this is a great question. Are these problems really hard? And the same question we have about factoring, and there's lots of work on that, and there's lots of progress. We have things like number field sieve, highly non-trivial algorithms. And I would say that for lattices, there isn't much progress. We have we have a relatively seems to be stable understanding of what one can do, and for many, many years there hasn't been, I would say 3 decades, there hasn't been true progress.
Not even say theoretically, just even practically. Like
In practice, right. I mean, there are websites you can download challenges, like in 500 dimensions. No one knows how to solve it. It seems like a really hard problem in concrete sizes, right?
Also, I mean, the empirical phrase in your question, I mean, you'll talk about that, I guess. I mean, you're not talking worst case complexity and so on.
Yes. Yeah, I mentioned this. Okay, so the distributions are well understood. This is something I'll get to in a point. Yeah, where to find the hard instances. Yeah. In some sense, they're everywhere, but you'll see what I mean later. So more recently, what I'd like to talk about here today is a problem called learning with errors problem, and this problem somehow abstracts away the lattice and gives you a very convenient, very pleasant thing to work with, and this problem can be shown to be as hard as lattice problem. So this is kind of an intermediary problem. The problem is as hard as lattice-based, as lattice questions, but it's extremely useful for crypto. You'll see what this problem is about in a slide. It's a very nice problem to work with. But kind of the funny thing, it kind of came from attempts to attack all these lattice-based crypto schemes using quantum computation. You'll see some of this later on. But it's actually, the problem itself has nothing to do with quantum computation. I just want to mention the history of this, which might still play a role in the future of this problem. And I think this crypto system is still the only crypto system where kind of ideas from quantum computation play an important, crucial role. Even though the system, you'll see, there's nothing quantum about it. It's kind of behind the scenes, but it plays a very important role, which is, I think, still not fully understood. So what's so good about this? Why bother about this? We have RSA. Everything is good with RSA. Why bother with other alternatives? So I'll try to give you 4 reasons why it's harder, better, faster, and stronger. So let's start with harder. It's provably secure based on worst case problems. So this is something I guess I can spend 10 slides on. I won't do it here. The idea is that when you take something like RSA and you break RSA, what you manage to do is factor, say, actually not even that, but say you manage to factor a certain number. What happens here is that once you break these schemes, you actually manage to break all instances of this lattice problem, not just a specific one, but actually all the instances of the lattice problem. There's some random random property of these lattices that once you solve one of them, you solve all of them. It's unique to this kind of systems at least in this very strong form. It's a very nice security property. It kind of tells you that it removes some parameters from the scheme. Like when you run RSA, you have to start thinking, how to choose the P and the Q. Should they be, like 1 modulo 4, 3 modulo 4, and so on and so forth. Here you don't have that ambiguity. The parameters are determined, they're kind of clear. Everything has to be, everything is already specified in some sense. And once you break the scheme with the parameters I give you, you immediately solve all instances of a given, all instances of the lattice problem. So this is something a bit delicate to explain in such a short time, but I hope you get at least some sense of what's in it. So this is a good, if you care about this, you can ask it. I'm happy to get questions on this. Okay, so the second thing, which some might dismiss as irrelevant, but I would contend that it is relevant. So far, these things are resistant to quantum computers, and in contrast, RSA and everything based on number theoretic assumptions is broken by quantum computers. So you might say, there are no quantum computers, but how sure are you in 10 years there won't be any quantum computers? And are you really willing to take the chance that in 10 years there won't be any public key crypto? There won't be any cryptography. This is just a news story from New York Times, like 2 months ago, or 3 months ago. IBM claiming they already essentially have a quantum computer. I think it is a bit of overhyping here, but they seem optimistic, saying that it's no longer 50 years away, it's only 15 years away. Yeah, but...
What's the largest number? 50.
I wish, yeah, I wish. It's, yeah, but I think they're going in the right direction, not trying to factor bigger and bigger numbers, but actually trying to come up with a scalable design. Once you have it, that you should be able to scale it to bigger and bigger sizes. But in any case, I think it's something humanity should have an alternative, and maybe this is this is maybe one way to go. So far, it seems resistant to quantum computers, despite attempts to break it. And the third thing, at least in some cases, these things can be faster than other constructions like RSA. I should be careful here. RSA is extremely fast. The advantage here is that there are no exponentiations needed. I'll show you later what goes into these schemes, but essentially just addition and multiplication, basic multiplication. So it might be in some applications, for some applications faster. And the last thing, last but not least, actually, I think it's a very nice, very important thing, is that this is only something we realized in the last 2 years. I'll talk about this later. You can do more things. You can do things we just didn't know how to do before, using anything, number theoretic crypto. And specifically, I'm referring here to this latest breakthrough on fully homomorphic encryption. I'll talk about this at the end. This is something that so far we essentially only know how to do based on lattices and based on this LWE problem. Okay, so questions so far before we get... Okay, so here's the one way to describe the LWE problem. It's not the way it's usually described. This is a way you can kind of a nice take-home message. You can keep it, keep this picture in mind. This is good. Actually, usually it's a slightly different form, but let me describe this anyway because I think it's cute. So, I give you a sequence of numbers, as many as you wish. I can give you, 2 billion numbers, and I tell you, say either the numbers are just uniform on the interval 0, 1, or that actually there are some close to some 1 over s for some number s. So actually they're close to some, actually there's some period, in this case period of 7 in this picture, where they're all close to that period, to 1 over 7. So example there on top, 0.154 and so on and so forth. Does anyone see? Do you see any structure in these numbers? Does it look like it comes from something like that, close to some? Okay. So they're all actually very close to 1 over 13. So I chose 13, so you won't immediately see that. But so if it's so hard with 13, you can imagine what happens when you take a bigger number. And this is essentially one version of the LWE problem. So there are several ways to phrase it. One way would be like to really ask you to find S. So there's, you can think of it in the following way. I just give you a sequence of numbers, AI, and I tell you that there's some number S, in this case 13, such that AI times S is close to 0, modulo 1. Okay? And you're supposed to either tell me that there is such an S, meaning it's not just a bunch of uniform numbers, or tell me what S is. I'm happy either way. This is essentially the problem. This seems to be hard. I'll tell you later what we know about the hardness of this problem. Let me also tell you the way it's usually stated. This is the way I'll use in this talk. It's usually stated in the n-dimensional way. The two things are essentially equivalent, at least for this talk. And the way it's usually stated, there's also some secret period, but we prefer to work with zq to the n. So there's vectors, n-dimensional vectors with numbers modulo q. That's the way usually it's presented. And the way it's presented is that usually there would be some secret S. Secret S is now n numbers modulo q. And what you're given is like approximate equations like that. I'm telling you, I take some uniform coefficients, AI, and I tell you either product of AI times S is essentially BI, or equivalently, once I subtract some number BI, it's close to 0. So essentially, I give you all these linear forms and tell you, I give you the AI, I give you the BI, I don't give you the S. But so you get all this list of equations and tell you, they're approximately correct. Can you just tell me what S is? Can you recover S from here? Maybe now it's a good time to say why is there this approximate? Why is there this noise in the equations? If there's no noise, then it's easy to solve, right? If there's no noise, I'll just give you a bunch of equations. You can recover S, right? You just do some kind of some Gaussian elimination. You recover S from equations. We know how to solve equations. The reason it's not trivial is because of this noise, right? Once you try to do anything with this, like Gaussian elimination, you have to combine equations. Then the noise starts, messing everything up.
There's no noise, can you still do Gaussian?
You can probably, then you can take, you don't need to recover S. You can take a prime, take everything modulo a prime factor of Q. I just want to say to tell this apart from uniform. Yeah, Q is small usually. Q is polynomial in N. But the factoring is easy, right? You have quantum computers then. Okay. Oh, you solved it.
No, sorry. I was just,
yeah. No, it's.
So the point is that you take modulo Q, right? Because if you didn't have that, if this was just over the integers, then it would also be easy.
So you can also do it over the integers, but you have to be a bit careful.
Excuse me?
You can do it over the integers, but you have to be careful. It's definitely cleaner when everything is modulo Q.
It's because it's discrete. If you take a continuous version, it's...
So you just, if you just completely remove the modulo here, you think it's going to be easier. Maybe you can tell something like
just
it's very big.
Squares, I think.
Okay. Right, but there are still ways to define it without the modulo Q that makes sense. We can think about this later. Yeah, it's one of the things about this. It's so versatile. So usually, unless you do something very bad, you can define lots of variants of this, and they all be secure. So what do we know about security of this? There are actually two main statements. And the first one, which I would say this is unfortunately still the only true security statement that we have, is the following. It says that this problem, LWE, is essentially as hard as n-dimensional lattice problems. I'm not being precise here, but essentially as hard as what's known as the shortest vector problem. The details don't matter, but it's essentially as hard as the worst case instances of these problems. What this means is if you break the problem, this LWE problem, if you break it, even with some small percent, some small probability, like 1%, you manage to find S, then you immediately get a solution for all lattice instances. Okay, not just a specific one, not related to the specific LWE instance you have. You immediately get solution to all the worst case, all instances of LWE, which is a very nice, very strong statement. The only caveat, which is unfortunately a big caveat here, is that this reduction is a quantum reduction. What this means is that if you break LWE, what the theorem tells you is that there is an algorithm for solving lattice problems, but it is a quantum algorithm. So if you think about it, it actually makes the statement weaker, because we would like to have as a conclusion, classical algorithm for solving lattices, but we get a weaker conclusion. We get only quantum algorithm for solving it, which makes it more suspicious. I mean, is it really secure for quantum algorithms? We believe it is. So far, there hasn't been any progress. As I told you before, these lattice questions seem to be secure. But I would really like to get rid of this quantum thing. Unfortunately, we don't know how to do this. It seems crucial in all these constructions. Luckily, there is a way around it. I mentioned here lots of works. Maybe the most relevant are the recent works by Chris Pikert from 2009, and more recently work with Brakersky, Langlois, Stele, and Pikert, based on Goldwasser, Kalai, Pikert, Vaikuntanathan. And essentially what this says, it says, okay, you can make it a classical reduction, but then you need to lose a square in the dimension. So you can say that, with some caveats, that LW of size n is as hard as worst case square root n-dimensional lattice questions, okay, with usual reductions. So this tells us that, at least even if quantum algorithms break LWE, then not all is lost. We still know that LWE of size n is as hard as square root n-dimensional lattice questions. It's not as nice. I mean, we would have to work with bigger size LWE, but it's something, we'll have something to work with. So, these are kind of the two main statements. Ideally, I would like to have something like the first statement without the quantum part. Unfortunately, we're not there yet. And it's a big mystery. I mean, this has been open for many years, and I really don't know how to explain this. There are several ways to interpret what's going on here. So I won't show the proof. I want to move on to applications. I should show at least you saw once how these things are used. But some of the ideas that go into all these proofs are things like blurring a lattice. So if you take a lattice and add Gaussian noise, you see what happens here is that slowly this Gaussian noise increases, and at some point it becomes essentially flat, essentially completely white. It's not really flat, but it's essentially so close to flat that you can't see it. It essentially becomes all white. I show another example here. I start with certain two-dimensional lattice, and I add Gaussian noise. Slowly these things increase even more. And at some point, it just becomes so close. This is a real simulation, and it's just so close to flat that you don't see any more the difference. This property is what makes all lattices the same. I mentioned before that if you break one, you break all. This is kind of what's causing it. That after you add enough noise, there's really there's no difference left between one lattice and another lattice. But of course, there's much more to the proof than this. But this is one idea that goes in there. Okay, so recently there's been lots of work on this. This is kind of something I stole from Chris Pikert, and the amount of papers, the number of papers on LWE, and here's a list. So there's been lots of work in crypto, especially lots of application. You take this LWE problem, which is it's kind of seems like a clean enough problem. It's very versatile. You can do tons of things with it. You can do normal public key encryption, CCA secure, for those of you who know what this is, identity-based encryption, and lots of other things. I'll tell you today about two things, just the basic public key encryption, and I'll try to tell you a bit about this newest and coolest thing, the fully homomorphic encryption, this work of Gentry and others. Let's see how far we get. Just to give you some sense of how one works with this LWE problem. It's so convenient to work with. I think it's nice if you see it. So here's how to create a public key encryption scheme. So just to recall, if you've never seen public key encryptions, the idea again, I have a way to choose a private key and a public key. I release the public key. Anyone else should be able, using the public key, send encrypted messages to me, and I should be able to recover them using my private key. Okay? So it's extremely simple. You just choose a random S in ZQ to the N. This is my private key. I keep it secret. No one else should see it. And the public key is all these pairs, AI, BI, and they are representing equations. AIS minus BI is essentially 0 with some noise, and noise is even noise. Okay, the noise is an even number. This is okay. You can assume the noise is some small even number.
Q is supposed to be odd?
Q is odd, yeah. So essentially what I'm releasing as a public key is a list, long enough list of such approximate equations. I tell you that, I give you AIBIS, I tell you AIS is essentially BI up to some even noise. Okay? Why is this useful? So here's how you as a person receiving the public key can send me encrypted messages. Assume you just want to send me a bit. You want to tell me just one bit of message. Okay, you can easily repeat this and send more bits. So what you do, you take all these approximate equations that I sent you, and then you just take a subset of them, a random subset of them, and just sum them up. So you have you take A2S minus B2 is roughly 0. A7S plus minus B7 is roughly 0. Just sum up this random subset of equations, and you end up with something like this. You have the sum of SAI, the sum of SBI, and I want you to add the bit x01 to the right-hand side. Okay. And why is that? If you think of what I essentially did here, but if you sum up equations that are all approximately correct up to some even error, the sum is also approximately correct. It's some small even number, the right-hand side. If I add x, if I add 1, then suddenly the error becomes odd and not even. And that's why I can later decode it. So here's how we decode it, how we decrypt. I'm receiving, you send me now this encryption, you send me this pair, A and B. And all I have to do is, I know S, right? I know the secret key. I compute the inner product of A and S. I subtract the B, and I see just if it's even or odd. I take the value modulo 2. That's all.
The A is the sum of the AIs.
A is this, right? This is the encryption, the first component in the encryption pair.
And I don't need to know this capital S?
You should not know. No, it's not sent. Yeah. Capital S is not sent, otherwise it will not be secure. So maybe the way to think of it is that the public key consists of all these approximate equations. AI times S is roughly BI up to even noise. You want to encrypt. You just take a subset of them, sum them up. You get another equation that's also approximately correct up to some even noise. And you send me that equation either as is or by adding a 1 to the right-hand side. Right, and I can plug in S, and I see that two things are close, but either even distance apart or odd distance apart. And I can therefore tell if you encrypt x01. Does this make sense? Okay. Those of you who've seen before, I'm writing in a slightly different way because I'm planning to use it later for the fully homomorphic encryption. Okay. Eli. So roughly 0 means that it's a small even number. This is the noise. So it's actually, the equations I release are never accurate equations. Otherwise it would be easy, it won't be secure. So a small even number is actually, to be precise, you have to choose it from typically some normal distribution. But it should be, in this case, should be even.
How big the public key should be for this?
Right, so you need, in this specific implementation, it's not the most efficient way to do it, but here you need n log q pairs. So the size of the public key is n log q times another n log q, I would say, for each equation. So like n squared, essentially n squared bit. It's not the most efficient way of doing things. Yeah. So let's just see, the decryption is like that, and correctness, essentially we argued already correctness, why this is correct decryption. The security, mainly for the experts, the way to prove security is in 2 steps. First you say that by the hardness proof of hardness assumption of LWE, we know that the public key, this list of approximate equations, just looks like a uniform random numbers. There's no structure that can be gleaned from the A and BI, just a bunch of random numbers. So we might as well replace them with random numbers. And then the second part says that if AI and BI are really random numbers, when you sum up n log q of them, that's why I need n log q of them, when you sum up a subset of size n log q of them, you essentially get uniform junk. You get uniform number, hence this x is completely hidden there. So this is, for those of you who've seen security proof, this should maybe ring a bell. This is the 2 steps in the security proof. It's a simple security proof. You just do, you first apply the LWE assumption that AI and BI completely look uniform. No one can tell the difference. It looks like a uniform junk. And then say that once they're uniform, there's really nothing encoded in the encryptions. Okay, so here's a second and last application. I think it's very nice. Later, recently it was in the headlines. This is work on fully homomorphic encryption, which allows to do this following almost unbelievable thing. You can send encrypted information to a server, say like Microsoft Azure or some other cloud server, and they do the computation for you on your data, and they send you back the result without ever seeing your data. So you have an encrypted information. You don't send the secret key to the cloud. They do the computation for you and send you back the encrypted information. Some applications of this, there are several ways to motivate this. Assume you have some secret information and you don't want to release this, but you also don't want to spend time computing it. Like you want to compute something on some DNA, do some analysis on the patient. You have some DNA information. You want to do some computation on it. You don't have the means to do the computation, but you also don't want to release that this private information. So you just send an encryption of this DNA. Some computer in the cloud can start processing it, computing something about DNA, about some risk of disease, and send you back the result. But the cloud never sees the information. The cloud never knows what computation on what the computation acts. It's kind of counterintuitive thing. Seems almost impossible. And actually, when it was first suggested, I believe it was conjectured to be impossible. But it turns out this is possible. And this was done, the first breakthrough was by Craig Gentry in 2009, and recently this work by Bakersky, by Kuntanatan, essentially using LWE and things I showed you here. And this is at least, this is very nice in theory, still it's very far from practice. I mean, these things are horrendously inefficient. So the amount of computation the cloud would have to do is so much bigger than the ratio between what you have to do normally and what the cloud would have to do is outrageously big. But at least in principle, this thing is possible, and there's a hope that in a couple of years maybe the theory will advance that we can actually do it. Eli, yeah.
Just LWE?
No, there's still some annoying part still. Yeah, essentially there's some cyclic security assumption that's the missing link, but. That's only one, right? Okay. Okay, so let me try to show you how you do this magic. It's slightly, I won't show you all the details, but just to show you how you start doing it. And in some sense, the first part I'll show you is very basic, and you might, people knew this 10 years ago, but somehow most of the magic will happen in the second part. You'll see what I mean. So here's how you start. You have this DNA you want to send to a server, to a cloud, to do the computation for you. You choose a secret key, and as before, the secret key is simply a vector, an n-dimensional vector with numbers modulo q. Very simple. So now I have my data, my DNA, x1 up to xn, is n-bit string, and I want to send this to the server. So I send encryptions of these bits to the server, and the way I would do it, similarly to what we did before, except we don't need all this summing up equation stuff because this is secret key setting. So I would just send n equations. So for each bit, I would encode it in the following way. I would choose randomly AI, and I would construct the equation AI times S minus BI is essentially 0, and the noise will be either even or odd based on the bit. So let me say this again. I have my sequence of bits. For each bit, I do the following thing. S is fixed. I choose AI uniformly. AI is chosen uniformly. And I just take the inner product of AI and S, and I choose BI so that AI times S minus BI is close to 0, but with some noise. I'm not going to make it exactly 0, otherwise it's easy to break. So I'll add some noise, and the noise will be either even or odd based on my bit. Okay. So far, this is just plain encryption. Let's see what the server, the cloud, can do with this information. So the cloud just gets to see AI and BI, right? S is hidden, but it gets all these AIs and BIs. So one thing the cloud can do, this is the easy part. The cloud can easily XOR bits, can add bits modulo 2. So how do you do that? I have this linear equation, A times S minus B. I have this linear form in S, A times S minus B, and have A prime times S minus B prime. So, and each one encodes a bit, meaning each one evaluates to either a small even number or a small odd number depending on the bit. All I do, I just add them up. So I add up the two things. I get a new linear form. I get A plus A prime times S minus B plus B prime. And you'll notice that if both have even noise, then I end up with even noise, right? If one is odd, one is even, I end up with odd noise, and if both are odd, I end up with even noise. In other words, XOR. Okay, we managed to do XOR of the secret bit without ever seeing the secret information, right? So this is the first part. This is the additive part of this scheme, which is always the easy part. The magic happens in the second part. So once we know how to add things modulo 2, how do we multiply things modulo 2? How do we do AND? How do we do the AND of 2 bits? Once we do addition and AND, we can do anything, right? The only question how to get to the other part. So let's try. Let's try to multiply 2 bits. Okay? So I want to do an AND of 2 bits. So the idea is this. I just, again, have 2 equations, and they each are either a small even number or a small odd number. And I just multiply them. So once I multiply them, I'll get a small, because the product of 2 small is still small. And it will be odd if and only if both are odd. Right? If one of them is even, the result is going to be even. So in that sense, it's OK. But the mess is kind of on the right-hand side. So I have this expression. Let's see what happens if I expand it. Let's start with the kind of easy part. So I have b times b prime. This is very good. These are scalars. So I have b times b prime there. The cross terms are also pretty good, right? I have, a in a product S times b prime. Pretty good, right? I can write it there. It's still some linear form on the S. And the only annoying part is kind of this part. This is what happens when you multiply a in a product S with a prime in a product S. Okay? The trouble here is if you think of it, so what is an inner product? It's simply sum of AISI, and this is sum of a prime j s j, and you multiply the two, you get, for all ij, you get ai a prime j si s j. That's what's written here. Okay. It's kind of
So just to remember, the server is doing all this by looking at a prime, b prime, but doesn't know s.
Correct.
Which is why.
So s is, think of s as being some kind of formula variable here. The server doesn't know what s is, but always plays with this formula variable. So this is just one way to write this expression here using tensors. If this helps, S tensor twice is simply the n squared dimensional vector of all inner products. It's just a fancy way of writing this. But okay, so it seems like maybe we're done. We have a way to, at least this way, it seems somewhat short. We have a way to write the product of 2 things. But actually, if you think about we're cheating here. Actually, we didn't make any progress because what's written here is actually a much longer expression, right? All these coefficients here, ai, aj prime, all this a tensor a prime, it's now I have to store n squared coefficients. I have to store all the ai, aj prime. So we multiply 2 things, sure, so we have a way to represent them, but it's actually terribly long. It's n squared bits long instead of being n. You might think, so what? But you have to repeat, you have to multiply more things. N squared becomes n to the 4, and n to the 8, and so on. So it explodes very fast. You really don't want this to happen. You don't want it to keep exploding more and more. This is where the trouble starts. So yeah, it increases the size of the ciphertext, and just ignore the comment there. And the solution, this is the ingenious solution. Solution says that maybe it's not so bad. Maybe the user, I can provide the server with some hints to help the server keep the calculation at bay. I don't want the server to have the calculation explode. What I'm doing, I'm providing the server with, and this is the ingenious idea, encryptions of SISJ using a new key S prime. So what this actually means, I have another key, another secret key S prime. I don't tell the server what S prime is, but what I do tell the server, I tell the server, here's Aij, here's Bij, some numbers. Actually, Aij is a vector, and I tell the server, Aij times in a product with S prime minus Bij is essentially this thing you're looking for, SISJ. Okay, so the server doesn't know SISJ. The server also doesn't know S prime, but I give the server this approximate equation. I tell the server, these 2 things are approximately correct. And why this is so useful is because now the server is stuck with this term containing n squared coefficients. The sum over ij, ai, aj prime, si is j. Now the server can replace each SISJ by the corresponding form, AIJ in a product S prime minus BIJ. And now if you think about this, this actually all collapses because this is just in a product of S prime with something plus a scalar. So this, what's written on the right-hand side is again of size n, not of size n squared.
And it's trying to encode the information given by A prime, A, B, A prime, B prime,
right.
Product of the two.
So we took the two things that are small, either odd or even numbers, we multiply them, we get another small number that's odd if and only if both are odd, which is the AND functionality, which is good.
But now the original thing was A times S minus B was odd or even. Now it's some other guy times S prime, which is a different variable.
Right.
Okay.
At the end of the day, the server sends you back this. You know S prime. You can still compute it and see if the answer of the DNA is positive or negative. You can still compute. You can decode at the end. The fact that you switched a key to a new key is, you still have the secret key. You can do it.
What happens if you do another multiplication?
So you need another key
as
double prime, right? Unless you do what's called the circular trick and you encrypt S under itself. And this is what you end up doing. This is what also we mentioned before. This is the extra security assumption that we need here. This is the only, the only thing that we don't know how to formally argue. With security, we don't know how to formally argue. At some point, we need to close this circle. Otherwise, you would have to provide more and more and more, which is also okay. I mean, for many applications, like if you have a low-depth circuit, you can do it this way.
So can you just sort of say roughly, so the notion of encoding under S prime, I mean S under S prime, will tell me how to take some secret, which is some bit which is stored relative to S prime, and convert it to some secret relative to S? Is that what you're saying?
That's essentially what it does, but it's more than this, because we provide you here not just with the, I could just do it for the SIs, and that will allow you to convert from encryption under S to encryption under S prime, but actually I provide you with more. I allow you to take quadratic things, SISJ, I essentially give you all the products of the coordinates of S, and still you can convert it to something in terms of the SI. Maybe I should say, just to make sure, because this wasn't, in case this wasn't clear, if you expand this expression, you should see there's, the S prime kind of comes out, and you get S prime in a product with some fixed n-dimensional vector. Okay, in case it's not obvious with all the indices here.
So this S, you're just finding the closest SISJ to that term on the left in that equation.
So how do I do that? So I know SISJ, right? I choose S prime uniformly, me as the user. I choose AIJ uniformly, then I calibrate BIJ to be close to SISJ. No, this is really scalar. This is a number, modulo Q. S prime is the n-dimensional vector modulo Q. I choose this uniformly, and I just have to choose a scalar here, so that the BIJ is essentially, this minus this plus some little noise. Actually, I'm cheating here. I won't give you more details, but actually, what I wrote here is wrong. But if you didn't see it, it's fine. The trouble is that the thing is, this is approximately that, but once you multiply by AI and AJ, these are big numbers. Actually, it is an easy, cute trick to go around this problem. But I think what I showed you here is, this does capture most of the intuition, I think, of these constructions.
You also had linear terms to deal with too, right?
You should also do the linear terms to move everything to S prime, right?
So if I understood correctly, when you add two bit streams, right, then the lowest level gets higher. So can you work around that?
So I didn't say anything about that. It's true. I said small plus small is small, but the other small is bigger than the former small. But you can't do too many. This is another big component I said nothing about. This is what Craig calls the bootstrapping. Once you have a way to do enough steps, you can kind of clean up everything and restart the whole process. Because there's trouble here that indeed the noise keeps growing. You need to at some point shrink it. And there's some beautiful ideas also in that paper by Bakersky and Vaikunthanath on how to shrink the noise. There are some very nice ways of doing that.
You shrink the noise without the help of the user at all.
You shrink the noise.
Without the help of the user.
Yeah, up to a point. Yeah, so this is a basic idea. The basic idea is just to divide everything. You have some modulus q, and you want to divide everything by 100. It seems like a very naive way of doing it, but it seems to actually work. So not divide in that sense, but actually think of the 0 up to q minus 1 as being mapped to 0 up to q over 100 minus 1. Kind of shrink everything by 100, kind of round to the nearest integer. There are other ways of understanding that, but this is... So I think, yeah, you don't need the user, but... right, okay. I don't think I can go into the entire construction, but there's lots of missing details. Yeah, we should wrap up. Okay, so I just mentioned what I said so far is efficient, but yet not most practical. And kind of recently, we've been trying to work on more really practical things by using some algebraic structures. We call this ring LW, and like all this fully homomorphic encryption, for instance, works also in this algebraic setting. Seems to make everything much more efficient. You can use fast Fourier transform, and everything shrinks. And it seems to be really practical. For the first time, we're talking about kilobytes and not megabytes. It has some nice, also lots of several nice theoretical aspects, but some other talk. Okay, thanks.
So let me start with this one. I mean, so as you mentioned somewhere in between also that, in homomorphic encryption, the big challenge seems to be that the work done by the server for every binary operation is huge. And is it really just sort of for every operation it's scaling large, or is there sort of further complications? If I have to do, n operations in a circuit, does the server do n times some fixed constant which depends on the security?
Good question. I think that's true, right? I think it's kind of each operation translates to something which is big, but it's not, the scaling is linear.
It's linear,
I think,
right?
Essentially, in fully homomorphic encryption.
It's n times something large in the security parameter.
Right, but the scaling asymptotically is linear. In principle, if I do fully homomorphic encryption, if I have n operations to do, the amount of work the servers do is n times something. It's not n squared or anything.
Yes.
And are there ideas on how one can get around that? I mean, can you
get around
n times something? What could you mean by saying, well, we want it to be more efficient at the server side?
Yeah, I mean, there's
the question is, what's the something, right? That's kind of
Right. It's how often you have to reduce the error term is the big thing.
Yeah, like what if you had a matrix multiplication or something?
Currently, we're kind of pulling the thread from too many directions. There's one thing, there's one thing I'm more familiar with. There are lots of aspects probably that I'm not so familiar with, but one thing in this construction is not so nice. It requires you to work with some super polynomial or things that are relatively large parameters, and that would be nice to get rid of. And I think this makes the practical parameters not so nice. So there's one place where efficiency would be much nicer, and so the theoretical equations that one could hope to improve that would lead to more practical schemes.
There's another big problem with these schemes. Often the ciphertexts are just really, really big. Like the way what Oded showed here, the basic idea, you encrypt one bit at a time. So for each bit, you send this, so you get really big.
So actually, there's work recently.
And then
Craig worked recently on working with more bits with one encryption.
So right. So it's now there's work in progress trying to improve these things, but that's another kind of dimension that's a big problem in practice.
It's still all very new, so I hope there'll be next few years there'll be some significant improvements, and maybe even become.
Like if you want to do a matrix multiplication, all you have to do is
like for specific, right? I think that's partly what they do. Like they consider specific tasks. I think that's partly what they do, trying to understand what kind of operations you can do. Like they have like seamed operation, like single instruction, multiple data, how to work in parallel. So for certain operations, they can do it more efficiently.
not more efficiently improving the constant or anything?
There's nothing to do but improve the constant. It's just linear times some constant.
So, yeah, I guess in practice you can think of it as improving the constant, but I think it's maybe more than that. I think they allow you to do operations like with a security parameter
as the constant. It's the the question is how much time in the security parameter. I mean, it's more than just.
Something this can be quite significant, but we're still not there. I think the only implementations currently available are for very small scale problems, and still the keys are huge and the ciphertexts are huge. So. Yeah, but there's hope.
Other questions? Andy?
Did you say that the learning with errors assumption is robust in the sense that you can also talk about or assume the hardness of like approximate linear equations over the real with no mods involved? Or is that too far?
Yes, he said it, but
did
he
I say
didn't mean it.
Yeah, so I think you could do something without the mod. Actually, that's funny. I think you can find this in some news group from the mid-90s. Someone suggesting something like this, which I think you can show.
There was a work actually of Craig Vinod and Chaya Levy maybe that did fully morphic encryption over the integers.
Yeah, that's essentially the first version of LW that I showed you. This is, I think, similar to the problem they were considering.
Okay, so there was also one
right,
over
but
the
still,
integers, there was no mod.
Oh, they had no mod.
No, they had no mod. Everything was over the integers.
So I didn't know that.
But
I was just curious, like following up on whether some linear equation solvers are based on sort of like starting with a guess and then iteratively trying to like reduce the error in your guess. And I'm just curious whether there's been any careful study of how well those things do on learning with errors.
I mean, you can make okay, depending on what exactly you make. I mean, the AIs, I guess. Okay, one of them can be made real, but the other one should still be discrete, right? So it's not. It's still a problem. There's still I think some discreteness left in there. Okay, we'd have to think about that.
All right, let's thank for dedicating.
Thanks.